So, today I will talk about linear algebra, convex sets and polyhedrons, because this is the basic mathematical concepts that we will need to develop the theory for the simplex algorithm and related topics. So, let me begin with, you may find it a little boring because we will be giving lot of definitions and a few lemmas and theorems, but I will try to give you examples so that the monotony is broken. Anyway, so let me just begin with, and most of these concepts maybe you have come across somewhere sometime, but let me just collate them together so that then we know what all the results we need, and I can keep referring back to them whenever I need them. So, I begin with, see, we all understand this symbol, this is Rn, and this is collection of all n tuples x1, x2, xn, right, where your xi's are all real numbers. So, if you take collection of all these n tuples, you get this Rn, and let us give it some structure. We already know, for example, that if I take two vectors, and for short I can call it this tuple as x1 to xn. So, I will sometimes refer to the vector as, so this will be, I will call it n tuple or a vector, and I will sometimes refer to the vector like this, or maybe like an n tuple, and later on I will also give you another shortcut. So, this will be, let us say, another n tuple, right, and they both belong to Rn. So, let us first assign operation on these n tuples or in these vectors. We say vector sum. So, I am defining an operation vector sum on Rn. So, I will say that x, this summation of the two vectors is nothing but component wise sum of the vectors. So, this will be x1 plus y1, x2 plus y2, xn plus yn. So, this defines the summation of two vectors, and geometrically you can see that if you have a two dimensional, that means I am talking of R2, you have been handling R2 and R3. So, if I have a vector like this here, let us say this is my vector x and this is my vector y, then you all know that by completing the parallelogram, this vector denotes x plus y. So, vector sum, you already have handled it, you know it, you have been using it. So, now if I extend this notion to an arbitrary n tuple, that means a vector having n components, then I just add them up vector wise, and here also you can see that the vector x, if this is written as x1, x2 and y is written as y1, y2, then the vector x plus y will have components x1 plus y1, x2 plus y2. Another operation that we define on this collection of n tuples or vectors, as we are calling them, is scalar multiplication. So, scalar multiplication of a vector by a scalar. And let me also make this clear, a scalar, when you say a scalar multiplication, what I mean is that the number is again a real number, it is coming from R, but it is not part of a tuple, n tuple, right. So, I will say that for C belonging to R and x belonging to Rn, we say that Cx is another vector which in which all the components get multiplied by C. That means, this will be Cx1, Cx2, Cxn. So, these are the two things, and even though I will not use this concept of vector space very often, still we will say that when you define these two operations, vector sum and scalar multiplication on this collection of n tuples, then Rn becomes a vector space. So, Rn is a vector space, right, and you see that 0 vector belongs to this, because 0 vector will have all components 0, right, and then you have this concept that if you add the 0 vector, it does not matter, here this is this, and this is equal to x. Also, when I define the vector sum, you see it does not matter whether I write x plus y or I write y plus x. Okay. So, this the concept, that means it is said that the vector sum is commutative, because the order in which you add the vectors does not matter here, because it is all component wise. So, whether I write x plus y or y plus x, it will be the same, fine, and so on. You can see all these things because we already are using them. It is all that we are now simply writing them in an axiomatic way. So, that what we are saying is that Rn, you can have more general concept of a vector space also, but we will not bother about it right now. Our concern is with Rn, and so we have these two, we equip Rn with these two operations and we will be using them. Fine. Now, you can have a concept of a subspace W of Rn. Okay. So, this, as the name suggests, it is a subset. W is a subset of Rn, which also satisfies the concept of which is closed under vector addition and scalar multiplication. What I mean to say is that you take W is a subset of Rn, right? That means the vectors in W are in Rn, fine. Now, if x and y belonging to W, the vectors implies x plus y also belongs to W, then we say that W is closed under vector addition, and also if this and Cx belongs to W for all C belonging to R and this belonging to W, then we say that W is closed under scalar multiplication. So, a subspace, a subset of Rn, if it is closed under vector addition and scalar multiplication, becomes a subspace, because it is also a vector space, and in fact one can in a very concise way say that W, a subset of Rn, is a subspace if Cx plus y belongs to W for all C belonging to R and x and y belonging to W. So, the same to both the things I have said in a concise way. So, this says that it is closed under vector addition and scalar multiplication, because I can put y as 0. If I put y as 0, then Cx bar belongs to W, that means the scalar multiplication is satisfied, and if I put C as 1, then x plus y belongs to W for all x y. So, this is the concept. Now, here you see that, for example, what we are saying is that in R2, so this is your R2, this is your R2, so the two collection of all two tuples. So, the whole space, that means you can say that the extend the blackboard in either direction, and this is what you get as the whole of your R2, right. Then if I simply say that my W, and here I now want to introduce the concept of linear combination. So, W, for example, can be written as, if I write this vector here, we are used to writing this as I and this as J. You have all come across vector algebra, you have done it in your school and so on. So, what I am saying is that if I take the vector I, this is my O, so the direction of I is this, then if I can describe the vector this subspace W or the subset W as all scalar multiples of this. So, that means of this direction I. So, here for example, I will take the number here which is equal to this length and then multiply it by psi I get this vector. I multiply I by a negative vector, I will get things on this direction. So, you see that the subspace here is the subset of vectors lying on this axis, right, and similarly this could be one subspace. Then I could also have a, if you take a direction like this, just take a vector here and you take the you can say this all scalar multiples of this vector, whatever you want to call it OP, then you take all scalar multiples of this vector, then you get a subspace, because it will be closed under, you see, if you take vector here and you take a vector here, then you add up, you will get a corresponding vector here only, right, because C1i plus C2i will give you C1 plus C2i and so on. So, I will continue to remain. So, therefore, the collection of the vectors here on this line, on this axis, is closed under scalar multiplication and vector addition. So, this is a subspace, right. So, I hope, see, actually we do not have time to dwell on too much on this thing, but just want to introduce you to the concepts, and you can we will be suggesting books for your supplement reading, and you can then look up there also these definitions. Okay. So, this gives us, now since I have allowed scalar multiplication, therefore, I can talk of linear combination of vectors. So, let me define a linear combination of a finite set of vectors a1, a2, ap, and we are assuming we are working in Rn. So, these p vectors are there, and then a linear combination will be defined as C1 a1 plus C2 a2 so on up to Cp ap for some C1 C2 Cp belonging to R. So, just take a set of p real numbers, and then you take this linear combination. This is what we mean by a linear combination of a finite set of vectors, right. Now, when you take collection of all possible linear combinations of these p vectors, that would be expressions of this kind, where C1 C2 Cp can be any set of p real numbers. So, this will be possible collection of. Now, you can immediately verify, and I want you to do this, that this set of all possible linear combinations is closed under vector addition, right. When you take two linear combinations, add them up, it will again become a linear combination of a1, a2, ap, and similarly it is closed under scalar multiplication also by definition, right. And then if you remember, these are the axioms that you require for a set of vectors to be a subspace, and so hence it is a subspace of Rn. So, this is the idea, right, and you can easily see that this is how you can also, given a set of p vectors, a finite set of vectors, when you take all possible linear combinations, you actually generate a subspace of Rn. So, this is the idea, and we will continue using this concept later on also. Yeah, and this is all you have been using somewhere in some way without actually calling them these names: vector space or subspace, scalar multiplication, vector addition. Vector addition you must have already talked about, because you use the parallelogram law, right. So, now I have this concept of linear independence of vectors, independence of a set of vectors. Okay. So, the idea here is that in some way I cannot make this, if I have a set of vectors and I want to find out whether there is a possible linear combination of this set of vectors which is equal to the 0 vector, right. So, that means here linear independence of a set of vectors. So, we say that a set A1 to AP is linearly independent if and only if I can use this small ai bar I varying from 1 to p, this equal to 0 implies C1 equal to C2 equal to Cp is 0. So, I was saying that if you have a set of vectors, and if you can and if some linear combination of this set of vectors equal to 0 implies that the scalars must all be 0. So, we say if and only if this and C1, C2, Cp are 0, then the set and the set A1 to AP is said to be linearly independent. Okay. So, it is said to be linearly independent. But if I can find certain scalars not all 0, you see the converse would be immediately, if I can find some scalars not all 0 such that so the corresponding linear combination is 0, then the vectors will be linearly dependent. Now, if C1 to Cp not all zeros can be found, then the set is linearly dependent. This is linearly dependent. And again the concept is very simple to understand, because what we are saying is, for example, here we are saying that if, say for example here, again let me go back to this thing, I can describe this tuple as for example, I can take, let us say, a vector OP here, and let me say that the components are 1 0, right, and let me take the vector here Q, and let me say that the components are 0 1, right. Then if I write a linear combination of these two vectors, it will be C1 times 1 0 plus C2 times 0 1, right, and say this is 0. Then if you compare, because obviously two n tuples will be equal if they are component wise equal. So here you see the vector that you get. So this implies that C1, so I am using scalar multiplication plus vector addition. So this vector becomes C1 0, this vector becomes 0 C2, then I add component wise, so I get the vector this, and this is 0 0. So which implies that C1 is 0 is equal to C2, and therefore the two vectors are linearly independent, right. But if I take a vector here and then I take a vector here, then you see this will be simply multiplying it by some negative scalar, and so the two vectors would be linearly dependent, right. And of course you can have so many concepts here. I have a vector here, and I have in 2 dimensions, you can immediately say that two vectors will be linearly independent if and only if one is not a scalar multiple of the other, because here if I take these two vectors, then obviously they are linearly independent, and so on. Yeah, okay. So once you define this concept, then we want to, because we now have linear combinations, we have concept of linear independence. Let me describe the situation. So I will now talk of a spanning set. Yeah, see, these preliminaries I will take time to explain, so that later on when we keep referring to them, there is no problem. So now what I will say is that if, see, for example, for this set, this is what I said was collection of all possible linear combinations of the vectors A1 to AP, then this set, this subspace, set of all linear combinations is spanned by the vectors. So spanned is the word which is underlined, by the vectors A1 AP, right. Span means that any linear combination of this set of vectors is here. So that is what we say, that if a set is spanned by a set of vectors, then that means that set has all possible linear combinations of the of that set of vectors. Okay. So this is spanned by the vectors A1 to AP, and so now what we are looking for example, for Rn, want to find the smallest spanning set. Okay, the smallest spanning set. So for Rn we want to find, because it will be very convenient when I want to refer to Rn, I do not have to write the, I keep saying that all collection of all possible n tuples. So I would like to have a nice representation for Rn through a spanning set, because once I know the spanning set, it is going to be a finite set, and then any vector in Rn can be obtained as a linear combination of this spanning set. So this is the idea. So we want to be able to represent the vector space in as precise a way as possible, and of course, so okay, so want to find a smallest spanning set, and this is what we are trying to now say, that for example, you look at the set Okay, so you take the vectors, take the special set, take the special set E1 En. Okay, some of you may be familiar with this notation, but let me say that E1 is the vector, is the n tuple which has a unit in the entry in the first place and zeros elsewhere. And similarly E2 will be a vector which has n tuple which has a unit entry in the second place and 0 all over. And similarly En will have this, right. If you have this collection, then if you look at any n tuple xn belonging to Rn, then this x can be easily written as x1 E1 plus xn En, right, because again you see scalar multiplication is valid, then vector addition I am using, and so from here you see you will only get the component x1, because all others will have 0 entries here in the first place. Then from the second one I will get x2 E2, I will get a x2 in the second place, and all other vectors have 0 in the second place, and so on. So this is what you have. So therefore I have found for you quickly a spanning set, okay. And you can also show that, so then this is this, that is the set E1, okay, I did not, but it is understood and sometimes I may forget, but this is the vector. So this is a spanning set for, is a spanning set for Rn, okay. Now is it the smallest one? This is the question, right. So I will show you that since, or okay, what I will try to say is that this is a linearly independent set, and therefore it has to be the smallest, or maybe that is not a good enough answer. I will have to show you in another way that this will be the smallest set. So that is the question, and maybe I will just not prove the result, but so is a spanning set. The set E1 to En is also linearly independent, okay, and that is easy to see by the same reasoning, because if I say that some linear combination of these vectors suppose is 0, then since this will become an n tuple, right, x1, x2, xn, so this has to be equal to 0 vector, so therefore that will imply that each of the xi's are 0, right. So the set is also linearly independent, easy to prove, right. I will say it is easy to prove, because if you take any linear combination of these vectors, you put it equal to 0, then component wise these scalars will turn out to be zeros, and so you are done, right. So therefore this becomes a linearly independent set, okay. Now of course again if we are bent upon mathematical rigor, then it is not enough to say that okay, this is the smallest set. What I will show you is that suppose, yes, so before that let me talk of the, and then I will give you some examples, replacement theorem. So replacement theorem says that if, let us say A1 or let us say Q, this is a linearly independent set, is a linearly independent set, and some A belongs to this linear combination, right, A1 AQ. That means A is a vector which can be expressed as a linear combination of the Q vectors, and A is this, that is A can be written as some C1 A1 plus CQ AQ, right, because A is a linear is a part of this. Therefore, I can find scalar C1 to CQ such that A1 can be written in this way, right. Now, if CR is not 0, see, it is not necessary that all the CIs are non-zero, some will be negative, positive, zeros. So, if CR is not 0, then A can replace, and that is why the replacement theorem, A can replace AR and the new set which is A1 AR minus 1 A R plus 1 AQ. So, this new set is also linearly independent. The new set is again linearly independent. So, now using this concept, that means what we are saying here is that if I express a vector in terms of a linearly independent set of vectors, then I can always replace the vector here in the base in the set for which the corresponding coefficient is non-zero. So, all I need is that if for example, C1 is non-zero, then I am saying that A can replace A1 and the new set that I get will again be linearly independent. Okay. So, you will have to accept this without proof, because in any case the proving part is not so important, it is the results that we will be using. So, this is it. So, now using this idea, what we can say is that if there are two spanning sets. So, I just now told you that we have a spanning set for Rn and it is also linearly independent. Now, what we want to say is that this is a precise representation for Rn, which means that I want to say that if, say for example, A1 to AP, yeah. So, this is this is Rn, which means that there are P vectors which form a spanning set for Rn, and the vectors AP are linearly independent, Similarly, suppose there is another set which is also a spanning set for Rn, and the vectors B1 to BQ are also linearly independent. Right. Then using the replacement theorem one at a time, what I can show you is that, again here we will not go into the proof exactly. What we can show is that, you see, for example, take A1. I will just give you a little idea about the proof. That I take A1. Since this is a spanning set, A1 can be expressed as a linear combination of these vectors, right, because this is a spanning set for Rn. So, any vector in Rn can be written as a linear combination of these vectors, and then there will be certainly some scalars which will be non-zero, because A1 is a non-zero vector, right. Why? Because remember, okay, when I introduced the concept of linear independence, maybe I should have pointed out that 0 alone is not a linearly independent set of vectors, right. By itself 0 cannot form a linearly independent set of vectors, and in fact any set of vectors containing the 0 vector cannot be linearly independent, Yes, clear? Because if you have the 0 vector, if you have the 0 vector, then what I can say, you take any set, let us say A1 to AR, and you take the 0 vector. This is not, I am not doing, okay, this is, this cannot be linearly independent. Why? Because you see, remember we said that there should be, if there is any linear combination of the set which is equal to 0, it must imply that all scalars are non-zero. But here you see, what can I do? I can choose C1 to CR as 0, but the coefficient for 0 I can choose as 1. So, then I have a collection of non-zero scalars. That means, I have a collection of scalars in which at least one of the scalars is non-zero, and the linear combination will give me the 0 vector. So, this cannot be linearly independent, right. So, I am using this concept. So, this was just a digression. I should have mentioned this earlier, fine. Anyway, so what we are saying is that here, if you take the vector A1, and this, since this is a spanning set, A1 can be written as a linear combination of these vectors. There will be at least one scalar which is non-zero, and so A1 can replace the corresponding vector here. Okay. So, similarly, I can go on with this process. I take the second vector, I can replace one of the basis vectors here, and so if P is less than Q, I am not going to write it down because I just want to explain this. If P is less than Q, then you see you will run short of, because you will have a set of linearly independent vectors here, and then you will have some extra ones, which must by definition be a linearly dependent set. Therefore, P cannot be less than Q, and similarly you can start the replacement process from here, and you will show that Q cannot be less than P. So, what we have shown is that P is equal to Q. Okay. So, by verbal argument I have shown that P is equal to Q. Using the replacement theorem, we have been able to show that P must be equal to Q, which implies that any spanning set, any linearly independent, let me say here, any linearly independent spanning set of R n must have the same number of vectors in it. Vectors in it. Okay. So, right now maybe the argument has been shown to you through a lot of hand waving, but does not matter. This can be found in any standard text. So, what we have said is that if there are two different spanning sets and the number of vectors is different, then it will contradict the definition of linear independence of one of the sets. So, the number of vectors in any two spanning sets which are linearly independent must be the same, and so this is what is it. And I already showed you a spanning set for R n which is also linearly independent and which has n vectors in it. E1, okay, I have been using this, E1 to En is a spanning set and also linearly independent. This implies any linearly independent spanning set for R n must have exactly n vectors in it, exactly because I already have one with n vectors. Therefore, any other spanning set which is linearly independent must have n vectors in it, right. And we say that a spanning set which is linearly independent is called a basis. Basis, it's called a basis, right? And number of vectors in a basis is the dimension. So I'll just take off from where we number of vectors in a basis will be the dimension of Rn. Okay. Rn is arbitrary, so therefore what we are saying is that whatever n will, so therefore the number n now has an important meaning, and that is it will always refer to the dimension of the vector space that we have taken Rn with this structure of vector sum and scalar multiplication. Rn becomes a vector space of dimension n, right? And we have said that any basis, any spanning set which is linearly independent for Rn will have the same number of vectors in it. So let us just look at the examples to illustrate the concepts that I have talked about here, and say, see if you can immediately see that if you take, let us say, these two vectors, these belong to R3, right? Then obviously these two vectors cannot form a spanning set, that is the vectors 1 0 0 0 1 0. If you take all possible linear combinations, this is not equal to R3, because what is happening, if I take a linear combination here of these two vectors and add them up, then the third component of the vectors in this subspace will be 0, which is not exactly R3, because the third component in R3 has to be any arbitrary number. So this is not equal to R3, right? If I take say this and any arbitrary vector here, yeah, if I take a 3, since 5 is present here, and so this combination you can show is R3. And what do we need to show here? We need to show two things, that this is a spanning set for R3 and it is linearly independent. Now you can immediately check, yeah, here for example, how will you check the independence? So suppose the set is linearly dependent. Okay. This implies there exist scalars C1, C2, C3 such that C1 1 0 0 plus C2 0 1 0 plus C3 1 3 5 is the 0 vector. Let us see, we will try to find the solutions here and see if C1, C2, C3 are non-zero or not. Okay. So the first, if you look at the first component, compare, then you get that C1 plus C3 is 0, then from here you get C2 plus 3C3 is 0, and from here you get 5C3 is 0, right. So this implies C3 is 0. If C3 is 0, from here you get C2 is 0, which, so if you go back upwards, then this implies that C2 is 0 and this implies that C1 is 0. So therefore the 3 vectors are linearly independent. Now if the 3 vectors are linearly independent, they have to form a spanning set. Figure it out yourself. Okay. It's very simple to, you can argue it out, that if I have, because I know that dimension of R3 is 3, so any linearly independent spanning set must have 3 vectors. So here if I have found already 3 vectors in R3 which are linearly independent, they must also form the spanning set. That means this is a basis for R3, right. Okay. And now if you want to look at the concept of replacement theorem, let me give it to you and I will revisit the concept of subspace also. Now for example, okay, look at this vector 0 0 1. So therefore this belongs to the span of right. So how do we find out that? Sure. I mean, how do we find out the linear combination? This we know, because this is the basis for R3. So, any vector in R3 should be expressible as a linear combination of the basis vectors. So, we want to say that find C1, C2, C3 such that yes, such that C1 1 0 0 plus C2 0 1 0 plus C3 1 3 5 is equal to 0 0 1. I want to express this vector as a linear combination of these three. So, again if you compare component wise, you get that C1 plus C3 is 0, then from here C2 plus 3 C3 is 0 and 5 C3 is equal to 1, okay, because the contribution from here is 0. So, 5 C3 is 1. This implies that C3 is 1 by 5. So, go back, this will imply that C2 is minus 3 by 5, yes, and from here this implies that C1 is minus 1 by 5. So, just verify that this is what you will get. C1 is, because C1 plus C3 is 0, C2 plus 3 C3 is 0 by choosing these values, and this. So, you have this linear combination. C1, C2, C3 are non-zeros. Okay. So, then by our replacement theorem, we have that this vector can replace any of the three vectors and you get a new basis. You get a new spanning set which is linearly independent. So, in fact, here I can get, because all C1, C2, C3 are non-zero, therefore, I can get three different bases by replacing. For example, I can replace 1 0 0 by this, I can replace 0 1 0 by this, and this. So, this is what gives you a feeling of, and of course, we all just need to be very familiar with the concept of linear independence and dependence and the concept of basis. Okay. A few lectures before, I had defined subspace for you, and the idea was that if there are two vectors in the subspace W, then Cx plus y is also in W for all C belonging to R, then W is a subspace of V. This was the definition I had given to you some time ago. Now, I would like to give you an alternate definition of a subspace, and which is a very convenient way of looking at a subspace, and that is that every subspace of V can be obtained as a solution space of a system of homogeneous linear equations. Okay. So, that is given a subspace W. Suppose I am talking of a subspace in Rn, and we can find an m by n matrix A such that the components are Aij, such that W can be written as all x which satisfy these linear equations, linear homogeneous equations, m of them. And so, the solution space now, of course, we have also seen that when you take a system of homogeneous linear equations, then this forms a subspace in Rn, if I am talking of in terms of n variables, then because the sum of two solutions will also be a solution, then a scalar multiple of a solution will also be a solution. So, that means that condition will be satisfied that for all x, y in W, Cx plus y is also in W for any real number C. So, therefore, the solution space here is a subspace. Now, of course, the whole idea is that how do you go about finding the matrix corresponding matrix A, and of course, there can be more than one such system of homogeneous equations for which the solution space is W. So, all those things are there, but we will not go into that, but I just want to give you an idea. And so, of course, the way you go, and then I want to relate the, because when you write down these equations, then you see the usual way of solving this system of equations is that you row reduce the matrix, you find the echelon form, row reduced echelon form of A, and because elementary row operations on the equations will not change the solution space. This also you know from your elementary linear algebra, and so here you will be able to reduce the matrix A in this form, where this is a R by R unit matrix, sorry, and these m minus R rows these are m minus r rows which are all zeros, and you have some non-zero entries here. So, immediately you can say that the rank of the matrix is R. That means the number of linearly independent equations is R. And then we know that because you have this identity matrix here, and you will have x1, x2, xn. So, immediately you will be able to fix the because the remaining, see here you will take the first variables x1, x2, xr, then xr plus 1 to xn, and you will be able to fix the r variables x1 to xr in terms of the n minus r variables, right. And then the number and therefore the number of linearly independent equations are r, and so the number I should say that the number of linearly independent solutions here would be n minus r. Why? Because you are expressing these r variables in terms of the n minus r variables, which are again if you use the language, we say that the n minus r variables are free to take any value, right. And so, the r variables get fixed in their values corresponding to the n minus r variables which are free, and so then I can find n minus r linearly independent solutions here. And so, the dimension of W, I mean this is the relationship, I will try to demonstrate it through some examples. So, dimension W is then n minus r, because I can find n minus r linearly independent solutions, right, and they will form the basis for W. Because then any solution in W, any vector in W is a solution and can be expressed as a linear combination of the n minus r linearly independent solutions that you will find by giving some values to the free variables, the n minus r free variables. So, this is the idea. So, now suppose I describe just take subspace W, which is described as follows, that this is collection of all vectors in R3 which are orthogonal to the vector 1, 2 minus 4. Okay. I am writing it as a row, but it is actually a column vector in R3, okay, but does not matter because of sometimes you do not want to take so much space. So, you write them as I mean this is common. Okay. So, this is my subspace. My description of the subspace is a collection of all vectors in R3 which are orthogonal to this vector, right, which means that I am looking for. So, the description of W now you see is immediately through one linear homogeneous equation. This is x1 plus 2x2 minus 4x3 is 0, because any vector x1, x2, x3 which is orthogonal to this must have its dot product with the vector equal to 0. So, x1 plus 2x2 minus 4x3 is 0. So, all x which satisfy this equation are in W. So, this is what I am trying to say, that you had one description of the subspace here, but then you can also give a description of W as a solution space of a system of homogeneous linear equations, right. And then what we see is that from here, yeah, this is what I want to explain, that if you have x1 plus 2x2 minus 4x3 is equal to 0, this implies that suppose I want to fix x1, this is minus 2x2 plus 4x3. So, what I am doing is I am putting x2 equal to 1 and x3 equal to 0. So, that gives me one solution. So, x1 becomes minus 2. So, I immediately get the solution minus 2, 1 and 0, because x2 is 1, x3 is 0. Similarly, if I put x2 equal to 0 and x3 equal to 1, then I get the second solution, right, because it will be 4 and x2 is 0 and x3 is 1. So, you see that the whole solution space or the subspace W is the linear collection of all linear combinations of these two vectors. It is a subspace, right, and since you had one linearly independent equation right here describing W. So, therefore, dimension of W is 3 minus 1 equal to 2. Right. And so, maybe some more examples I will try to give you a feeling that how you, of course, this is a little going a little away from the topic, but essentially I just want to make you feel comfortable with the concept of dimensions and so on, and therefore, I am spending a little time here trying to show you that how you can look at subspaces in terms of as a solution space of system of linear equations, and then derive the dimension of the subspace from there. Let me just spend a little time on this. What we are saying is, see, you have learned this, that say x1 plus x2 plus 3x3 is equal to 0 and minus x1 plus 2x2 plus x3 is equal to 0, right. How do you solve this system 2x2? You have learned this method of elimination, okay, that is the right word, method of elimination. Say for example, here I add up the two equations. What do you get? 3x2 plus 4x3 is equal to 0, right, which gives you that x2 can be written as minus 4 by 3 x3. So x2 can be written as 4 by 3 x3. Now I substitute here the value of x2, then I get this. This gives me x1 minus 4 by 3 x3 plus 3 x3 is 0, which implies that x1 is equal to, so here 339, which is 5 by 3. So this is minus 5 by 3 x3. Okay. So therefore I have been able to, in this system I have two equations, three unknowns x1, x2, x3. I am considering the system of equations in R3, and you see that here the best I can do is I can determine x2 in terms of x3 and x1 in terms of x3, because these two equations are given. So there is another way of saying that you have the degrees of freedom for this system of equations is 1, because only one variable is free to take any value, and correspondingly the values of x1 and x2 get fixed, and so I have a solution. So let me give you the general solution here, because these concepts of dimensions and so on have to be understood clearly. So here for example, what is your general solution? x1, x2, x3. A solution to this system can be written as minus 5 by 3, x2 is minus 4 by 3, and this is 1, and I multiplied by x3, you see. So the solution space to this system of equations can be written as a scalar multiple of this vector, you see that. And so the combination, that means if I write W as the solution space, then this is the linear combination of the vector 5 by 3, 4 by 3 and 1. So any solution, and of course you know that this, you already know that if you have a system of equations, I have been using the word, it is a solution space, that means I have been calling it a vector space, and we know that if x1, x2, x3 is a solution and y1, y2, y3 is a solution, then the sum will also be a solution. Any scalar multiple of this solution vector will also be a solution. So therefore this is a subspace, and here I have shown you that if the system of equations, if the dimension or if the rank or whatever you want to call it, the number of, or you can say that the number of equations is linearly independent. So if the number is m and you are talking in Rn, then the solution dimension of the solution space is n minus m. So in this case it is 1. Why is it 1? Because the spanning set contains only one vector, right? It is a non-zero vector, so it has to be linearly independent. This is another thing. See, a singleton, a set containing a singleton non-zero vector will always be linearly independent, right? So the whole solution space can be represented as a linear combination of scalar multiple of this vector, right? Okay, so I think this the subspace is there. Yes. Now I think I can just equip something more to Rn to make it a more useful space, and that is inner product, which again you have been inner product. Up to R3 you have been already using this concept of inner product. So we say that two vectors x dot y. So between two vectors x and y, I define this. This is the inner product or the dot product between x and y, and is defined by equal to summation x I y I varying from 1 to n. So component wise product and then add up. So, the inner product is defined as this. The inner product has the distributive property also, by which we mean that if you take the dot product between the vector x and c y plus z, where c is a real number, any real number, then you can when you can open up the brackets and you will have c x dot y bar plus x dot plus z bar, and this is true for all x y z in R n and all c in R. So, the distributive property is there. Then with the help of the inner product, we can define the norm or the length of a vector, and it is done by taking the inner product of the vector by itself and then the under root. So, the norm or the length of vector x is given by this number, right, and you can show immediately, because you have real numbers. So, sum of squares of real numbers, if it is 0, then each number must be 0. So, that means norm x 0 if and only if, this stands for if and only if, short form IFF, if and only if x bar is 0. If the vector is 0, the norm is 0, and if the norm is 0, the vector must be 0. Okay. Now, you can easily show using this definition that if you take the norm of the vector c x, c is a real number, then this come out as absolute value of c. That means the positive part, because remember, I should have said here also that this is greater than or equal to 0, because it is you are talking of real numbers and then taking the under root. So, that must be a non-negative number. So, here this has to be absolute value of c times the norm of x, right, and then this the triangle inequality, which also you can sit down and prove by yourself, that norm of x plus y will be less than or equal to norm x plus norm y, right. That means, if you take a triangle, if you take two directions with vectors x and y and length norm of x and norm of y, then you can show that the third side must be less than or equal to the sum of the two sides, the length of the third side, right. Then we can also have a concept of an angle here, and that is the Cauchy-Schwarz inequality helps us to define concept of an angle, and that says that if you take the absolute value of the dot product between two vectors, then that must be less than or equal to the norm of product of the lengths of the two vectors. Okay. And then with the help of this, we can define the angle cosine theta. So, the absolute value of cosine theta would be this number divided the inner product, absolute value divided by the two norms, you see. So, therefore, in other words, if you just want to define cos theta, it will be equal to x dot y divided by the norm x norm y. Okay. And so, this is less than or equal to 1, because of the Cauchy-Schwarz inequality. Okay, I have written that here. So, Cauchy-Schwarz inequality implies that the angle, the absolute value of the angle would be less than or equal to 1. So, it makes sense to have a concept of an angle here also in n dimensional Euclidean space, and then we immediately say that if this dot product is 0, then x and y are orthogonal to each other. So, through this these definitions, we have tried to show you that the structure of R3 that you are very familiar with goes through to Rn in most of the concepts, right, and therefore, you can Rn, you can feel very familiar with the Rn space. Okay. And the whole idea here, of course, in the next lecture I will continue with some more definitions and introducing concepts which you will need, like convexity and the polyhedron and so on, and you will see that with this background, you will have a better insight into the simplex algorithm, right. And so, this is the whole idea, that because essentially the algorithm developed through geometrical concepts, I always feel that it is important that you must be able to understand why certain things were done and why the algorithm took particular shape. So, it will help you if we go through a bit of the mathematical concepts that are needed for understanding the algorithm. So, I set out to give you concepts of linear algebra, then would also want to. So, I think in this lecture we have almost covered everything that I think will be needed from linear algebra, and of course, hopefully, if there is something left out, you can supplement it through books, or I can come back to them later on. So, the next lecture I will try to now introduce the concept of convex sets and polyhedrons, which are very essential for giving us a geometrical picture of the simplex algorithm that we want to develop and analyze for solving linear programming problems.